April 15, 1942. Petroleum Warfare Department Headquarters, London. Chief Engineer Arthur Clifford Hartley stood before a conference table scattered with technical drawings, his hands trembling slightly as he absorbed what the assembled experts had just declared. Impossible. That was their verdict on Vice Admiral Lord Louis Mountbatten's proposal to lay an oil pipeline across the English Channel. 50 miles of treacherous water, unpredictable tidal currents, German U-boats and Luftwaffe bombers prowling the waters, and somewhere on the other side, an Allied army that would need over 1 million gallons of fuel per day, or face complete annihilation. Hartley had spent 15 years laying pipelines across the mountains of Iran for the Anglo-Iranian Oil Company. He'd pumped 100,000 gallons daily through 3-inch pipes at pressures that would make most engineers' blood run cold. And now, listening to the collective wisdom of Britain's finest minds declare this channel crossing impossible, he felt something stir in his chest. Not doubt, certainty. "I believe it can be done," he said quietly. In that moment, Operation Pluto was born, an engineering feat so audacious that General Dwight D. Eisenhower would later declare it second in daring only to the Mulberry Harbors. He would add that the pipelines provided our main supplies of fuel during the winter and spring campaigns. For Eisenhower, Pluto wasn't a footnote to D-Day. It was a critical chapter. What followed would be 26 months of failures, breakthroughs, near disasters, and quiet triumphs that would ultimately deliver 180 million gallons of fuel to the Allied forces, all flowing invisibly beneath the English Channel, completely undetected by the Germans. The project would cost $4.4 million, a staggering sum in 1940s currency. It would employ over 1,000 sailors and naval officers. It would involve engineers from 3 oil companies. It would require custom-built factories at Tilbury. It would demand the conversion of Liberty ships into specialized cable layers. It would spawn floating drums weighing 1,600 tons each, and it would remain classified for 30 years after the war ended. This is the story of how engineers built the world's first floating pipeline. By April 1942, the British War Office had calculated a terrifying equation. Any successful invasion of Nazi-occupied Europe would require the largest amphibious assault in human history. Hundreds of thousands of troops, tens of thousands of vehicles, and fuel, staggering, almost incomprehensible quantities of fuel. The War Office estimated that petrol, oil, and lubricants would account for more than 60% of all supplies by weight required by the expeditionary forces. A single armored division, advancing just 100 miles, consumed approximately 25,000 gallons of fuel. The figures were staggering when extrapolated. General George Patton's Third Army would eventually consume over 800,000 gallons per day during its rapid advance across France. The entire Allied expeditionary force would require upwards of 1 million gallons daily, and that number would only grow as the armies pushed deeper into Europe. Multiply that across an entire army group, and the mathematics became brutal. Without fuel, tanks became metal coffins. Without fuel, trucks became immobile obstacles. Without fuel, the liberation of Europe became impossible. The conventional solution was oil tankers, massive vessels that could transport thousands of tons of fuel across the Channel. But conventional solutions had conventional vulnerabilities. German U-boats and E-boats prowled the Channel's confined waters. The Luftwaffe maintained constant aerial surveillance. A single successful attack on a fuel tanker could incinerate thousands of tons of desperately needed petrol while choking the invasion beaches with burning wreckage. Weather posed an equal threat. The English Channel's notorious storms could delay tanker convoys for days. And those tankers were desperately needed in the Pacific Theater, where American forces were island-hopping toward Japan. Every tanker allocated to Europe meant one less for the Pacific. Then there was the beach problem. The Normandy landings would already be chaotic, hundreds of thousands of men, vehicles and supplies flowing across narrow stretches of sand. Tankers required port facilities. Damaged ports meant delays, and delays meant German counterattacks. Lord Louis Mountbatten understood this equation better than most. As Chief of Combined Operations, he was responsible for planning the impossible, the invasion of Fortress Europe. His nightmares weren't about bullets or bombs. They were about fuel gauges reading empty. In April 1942, he approached Geoffrey Lloyd, the Secretary for Petroleum, with a question that seemed almost absurd. Could an oil pipeline be laid across the English Channel? Lloyd consulted his experts. Their response was unanimous. Impossible. The channel was too deep, the currents too strong, the pipes too heavy, the distances too vast. No technology existed for such an undertaking. But Mountbatten wasn't asking for opinions. He was asking for solutions. And Arthur Hartley, visiting the Petroleum Warfare Department that very day, overheard their conversation. Section 1. The Impossible Made Possible. Hartley's proposal arrived like a bolt of lightning. The experts had been thinking of conventional pipelines, rigid steel tubes, bolted together section by section, lowered carefully into position. Hartley proposed something radically different. Forget sections. Build the entire pipeline as one continuous length. Forget rigid pipes. Make them flexible, like submarine telegraph cables. Forget slow, careful positioning. Lay the pipeline at speed, using the very cable-laying ships that had already proven themselves in the Atlantic. The man proposing this wasn't some armchair theorist. Arthur Clifford Hartley was born in Hull on January 7, 1889. He graduated from Imperial College London with a degree in engineering. During World War I, he'd served as a major in the Royal Flying Corps. He was a qualified pilot. He worked on the development of interrupter gear, the mechanism that allowed machine guns to fire through propeller blades without destroying them. His war work earned him appointment as Officer of the Order of the British Empire. After the war, he spent 5 years as a consulting engineer before joining Anglo-Persian Oil Company in 1924. By 1934, he was their chief engineer. When he spoke about pipelines, he spoke from decades of hands-on experience. His logic was elegant. In the hilly terrain of Iran, Anglo-Iranian had employed 3-inch pipelines. Running at 1,500 pounds per square inch pressure, these pipes delivered 100,000 imperial gallons per day, the equivalent of over 20,000 jerrycans. The channel was flat compared to the Zagros Mountains. The currents were predictable compared to Persian mountain streams. The temperatures were moderate compared to Persian extremes. If he could pump oil through the Persian highlands, he could pump it through the English Channel. Hartley had experience that few others possessed. He'd been chief engineer of Anglo-Iranian since 1934. Before that, he'd worked in Iraq and Persia. He understood pipelines not as theoretical constructs, but as living systems. He knew how metal responded to pressure. He knew how oil behaved at different temperatures. He knew what could go wrong and how to prevent it. On April 15, 1942, Hartley pitched his proposal to the Petroleum Warfare Department. His concept was deceptively simple. Create a pipeline similar to a submarine communications cable, but without the core and insulation. Instead, fill that core with oil. Surround it with armor strong enough to withstand the internal pressure. Deploy it using cable-layer ships that could lay miles per hour rather than feet per day. By using high pressure, the same line could carry different fuels: petrol, diesel, aviation spirit. At low pressure, different fuels would mix. At high pressure, they would stay separate, a chemical miracle that meant one pipeline could serve multiple purposes. Hartley received immediate support from Sir William Fraser, chairman of Anglo-Iranian and petroleum advisor to the War Office. Fraser was a powerful ally. As petroleum advisor to the War Office, his word carried enormous weight. As chairman of Anglo-Iranian, his company had the technical resources and financial backing to make the project viable. More crucially, Henry Wright, managing director of Siemens Brothers, agreed to develop the cable technology. Siemens had decades of experience with undersea telegraph cables spanning the Atlantic. They understood the brutal conditions of the ocean floor. They knew how to build structures that could withstand crushing pressure, corrosive saltwater, and constant tidal movement. Their expertise in submarine cable technology would prove invaluable. Fraser committed Anglo-Iranian funds to the trials, gambling that the government would eventually reimburse the company. It was a calculated risk based on patriotism rather than profit. If Pluto failed, Anglo-Iranian would absorb substantial losses. If it succeeded, the company would be reimbursed, and the war effort would be advanced immeasurably. Fraser chose his country over his balance sheet. His gamble would eventually pay off, but in April 1942, success was far from certain. The project was given the code name PLUTO, which stood for Pipeline Underwater Transportation of Oil, or Pipeline Under the Ocean. The operation was placed under the Chief of Staff to the Supreme Allied Commander, designate Cossack. This meant Pluto had top-level priority. It wasn't a peripheral project, it was central to invasion planning. The G4 section of the Cossack staff assumed responsibility for Pluto. British Major General Neville Brownjohn headed the section. American Colonel F. L. Rash served as his deputy. Colonel Frank M. Albrecht succeeded Rash. Major General Robert W. Crawford succeeded Albrecht. The succession of American deputies underscored the joint nature of the operation. This was an Allied effort. British engineering, American industrial capacity, combined operations expertise. Royal Navy Captain John Fenwick Hutchings from the Admiralty's Department of Miscellaneous Weapons Development was placed in command of the operational forces. The Department of Miscellaneous Weapons Development was itself a fascinating organization. Known informally as Wheezers and Dodgers, these were the inventors, the unconventional thinkers, the men who developed weapons that didn't fit standard categories. Pluto was exactly their kind of challenge. By VE Day, Hutchings' command would consist of several ships, over 100 merchant navy officers, and more than 1,000 men. The operation had grown from a single engineer's proposal to a full naval flotilla. The race against time had begun. Section 2. Building the impossible pipe. The first problem was the pipe itself. Siemens Brothers, working with the National Physical Laboratory, began developing what would become known as Hayes cable, Hartley Anglo-Iranian Siemens. The design started from the inside out. At the core, a 2-inch diameter inner pipe made from extruded lead. Lead was chosen for its flexibility and resistance to corrosion. Around this lead core, a layer of asphalt and paper impregnated with vinylite resin for insulation. Around the insulation, steel tape wound in spirals to provide strength and flexibility. Multiple layers of steel tape, 4 layers in the final design, each wound at precise angles to maximize tensile strength. Another layer of jute tape and asphalt-impregnated paper for protection. And finally, 50 galvanized steel wires wrapped around everything, covered with camouflaged canvas. Each wire was precisely spaced. Each wire bore a calculated percentage of the total load. Each wire provided redundancy. If one failed, the others would hold. Each mile of this cable would weigh approximately 55 long tons. Each mile would require over 46 tons of lead alone. The lead consumption was staggering. Britain's church roofs were being stripped, medieval monuments were sacrificed for war production. Every ounce of lead mattered. The specifications were staggering. The pipe had to withstand internal pressures of 1,500 pounds per square inch. It had to flex enough to be coiled in a ship's hold without cracking. It had to resist the crushing pressure of deep water. It had to survive anchor drags, underwater explosions, and the constant stress of tidal movements. In May 1942, a 120-yard prototype was laid across the River Medway by the post office cable ship CS Alert. The pumping test began. After 2 days of continuous operation, the pipeline failed. Engineers hauled it up and discovered the problem. Lead was extruding through gaps in the steel tape. The steel tape wrapping was doubled from 2 layers to 4. The revised design worked. June 1942 saw deeper trials in the Firth of Clyde, Scotland. Siemens brought in Henleys as a second manufacturer to increase production capacity. Both companies' pipes performed flawlessly. The Clyde trials showed critical requirements: internal pressure of about 7 bar, 100 pounds per square inch, had to be maintained at all times, even during manufacture. This constant pressure prevented the pipe from collapsing under its own weight. It kept the lead core properly formed. It ensured structural integrity throughout the process. The testing revealed another crucial insight. Both pipelines were completely successful, and Pluto was formally brought into the plans for the invasion of Europe. The project received an official assessment that would prove prophetic: strategically important, tactically adventurous, and from the industrial point of view, strenuous. Every word would prove accurate. Strategic importance: the invasion depended on fuel supply. Tactical adventure: nothing like this had ever been attempted. Industrial strenuousness: the manufacturing would push British industry to its limits. Full-scale production of 2-inch pipe began on August 14, 1942, using steel from the Corby Steelworks. But then engineers realized a critical flaw. 2-inch pipe wasn't enough. To pump the required volume of fuel would require too many parallel lines. The decision was made to upgrade to 3-inch diameter pipe. Each 3-inch pipe had more than twice the capacity of the 2-inch version. Fewer pipes meant fewer ships. Fewer ships meant less chance of detection. Fewer pipes meant faster deployment. The engineering was sound, but lead was in desperately short supply. Churches across Britain were being stripped of their roof lead for the war effort. The amount required for hundreds of miles of high-as cable would be prohibitively expensive. The numbers were sobering. To lay pipelines from the Isle of Wight to Cherbourg, just the first phase, would require over 700 nautical miles of cable. At 55 long tons per nautical mile, that meant over 38,000 tons of cable. The lead alone would consume more than the country's church roofs could provide. And there was another concern. What if the HAI's technology failed in actual combat conditions? What if the lead extruded through the steel tape again? What if German depth charges ruptured the thin walls? A backup was essential. The consequences of single-point failure were too catastrophic to contemplate. A backup was needed. Section 3. The Hamel Alternative. Enter Bernard J. Ellis, Chief Engineer of the Burma Oil Company. Ellis had been closely monitoring the HHAI's development and noticed something fascinating about the cable. It was extremely stiff in short lengths, but flexible and manageable in long lengths. This observation sparked an idea. If lead cable could flex in long lengths, why not steel? Ellis had seen samples of small-diameter steel pipes in the oil fields of Iraq and Burma that exhibited the same property: rigid in short sections, remarkably flexible over long distances. He proposed abandoning lead entirely. Replace it with mild steel, cheaper, more available. and potentially just as effective. Ellis teamed with H.A. Hammack, chief engineer of the Iraq Petroleum Company. Together, they designed a new pipeline. The collaboration was productive, but not without tension. Ellis contributed the core concept and the broaching tool design. Hammack brought expertise in field operations and testing. After the war, Ellis successfully asserted his claim as sole inventor. The legal proceedings were complex. Hammack disputed the claim, but the Royal Commission on Awards to Inventors ultimately awarded Ellis $5,000, significantly more than Hammack received. The credit controversy was real, but it didn't diminish the engineering achievement. Both men contributed essential elements. Without Ellis's concept, there would have been no steel pipe alternative. Without Hammack's field experience, the pipe might never have been successfully deployed. History remembers them both through the codename Hamel. The pipe was 3.5 inches in diameter with 0.212-inch wall thickness. Prototypes were fabricated by J&E Hall of Dartford in 30-foot lengths. These segments would be flash welded together. Normal welding created rings of residue around each joint. Potential weak points. Ellis designed a special broaching tool to remove the metal swarf after each weld. The pipe was codenamed Hamel, from Hammack and Ellis. Though after the war, Ellis successfully asserted his claim as sole inventor. The credit controversy was real, but the engineering was undeniable. Testing proved the Hamel pipe had sufficient wall thickness to handle the necessary pump pressure. It could be bent around a wheel of 30-foot diameter and pulled off again without damage, and it was cheap, built from readily available materials at a fraction of the Haas cost. But Hamel had one critical problem. Unlike flexible Hay-Eyes cable, Hamel pipe couldn't be coiled in a ship's hold. The conventional coiling process introduced a complete twist into each turn of pipe. While laying, this twist would be removed during uncoiling. Lead cable tolerated this treatment. Steel pipe did not. The twisting would cause catastrophic failure. Ellis proposed a solution that bordered on genius: a large wheel mounted on trunnions on the deck of a hopper barge. The wheel's lower portion would protrude through the hopper doors into the sea. As the barge moved forward, the pipe would unwind directly into the water. No twisting, no coiling stress. Direct deployment. But the Petroleum Warfare Department went further. They proposed a floating drum, like a gigantic cotton reel, capable of carrying any quantity of pipe required. Model tests were conducted at the National Physical Laboratory's tank at Froude. The tests confirmed that such a vessel could be towed at sufficient speed without yawing. The drum was christened with a name that captured both its engineering purpose and the puzzling challenge it represented. They called it the conundrum, cone-ended drum, or perhaps the puzzle that kept engineers awake at night. Either way, the name was perfect. Section 4. The cable ships. While the conundrums would carry Hamel pipe, the flexible Haas cable required a different approach. Existing cable-laying ships weren't large enough. Their loading and laying gear wasn't sufficiently powerful or robust. The solution: convert merchant ships into specialized pipe layers. The conversion process was extensive. Ships were stripped of their interiors. Large cylindrical steel tanks were built in to store the cable. Special hauling gear was designed and installed. Suitable sheaves and guides were fitted to control the cable's movement. The Petroleum Warfare Department contracted Johnson and Phillips Company for the specialized equipment. This company had experience with undersea communications cables. They understood the delicate balance between flexibility and strength. As the pipe couldn't be bent to a smaller radius than 5 feet without damage, a new haul-off drum of 10 feet diameter was produced. A fleeting ring was added. Roller-type bow and stern gear were developed. Every piece of equipment was custom designed for this single operation. HMS Holdfast was the first converted vessel. Commander Henry Treby Heal OBE, RNR, took command. His crew would become the pioneers of cross-channel pipeline laying. HMS Algerian was acquired and converted to carry 30 miles of 3-inch cable pipe. 2 more vessels would become the workhorses of Operation Pluto. HMS Sancroft and HMS Latimer were converted Liberty ships. These were the mass-produced cargo ships that had become the workhorses of World War II. Sturdy, reliable, and plentiful. Each ship displaced 12,220 long tons. Length between perpendiculars, 425 feet. Single-screw propulsion. Each could handle 100 miles of 3-inch pipe, weighing approximately 6,400 long tons. 2 50-foot diameter storage tanks, one forward, one aft, provided the stowage space. The rudders were enlarged by fitting extensions to improve maneuverability during the slow, precise work of cable laying. Thames barges were also converted for shore-end connections. The main ships couldn't operate in shallow coastal waters. The barges would connect the final sections, working in the surf zone where precision mattered most. Royal Navy Captain John Fenwick Hutchings was placed in command of the entire Operation Pluto force. By VE Day, his command would consist of several ships, over 100 merchant navy officers, and more than 1,000 men. These men were based primarily in Southampton. They trained relentlessly. They practiced cable laying in the Solent. They perfected shore-end connections. They prepared for an operation unlike anything in naval history. Section 5. The Conundrums. 6 conundrums were constructed. Each was 60 feet long and 40 feet in diameter. Empty, they weighed 250 tons. Fully loaded with 90 miles of 3-inch Hamel pipe, each conundrum displaced 1,600 long tons. The cost, $30,000 per drum, approximately $1.5 million in modern currency. They were fabricated in Scunthorpe, erected at Tilbury Docks, and launched into the Thames. The naming convention was straightforward: HMS Conundrum 1 through HMS Conundrum 6. They were given ship names because they would effectively be vessels, towed by tugboats across the channel, trailing pipeline behind them like massive mechanical jellyfish. The loading process was an engineering marvel. Stewart's and Lloyd's constructed 2 factories at Tilbury specifically for Hamel production. 40-foot lengths of pipe were welded together into 4,000-foot segments. The welding was automatic, with pipe sections moving along conveyors from welder to smoothing tool. Women inspectors examined every joint at the end of each conveyor. Quality control that could mean life or death for thousands of soldiers. Their eyes caught defects that machines missed. Their attention to detail was legendary. Not one faulty weld passed their inspection. The factories operated around the clock, 3 shifts, 7 days per week. Production targets were aggressive: 16 kilometers of pipe manufactured daily. The British accumulated a stockpile of 550 kilometers of Hamel pipe. For Hayes cable, production was split between British and American manufacturers. Of the 710 nautical miles of Hayes cable produced, 570 nautical miles came from UK firms. 140 nautical miles was manufactured in the United States by 4 American companies. The transatlantic cooperation was essential. British firms couldn't produce enough lead pipe alone. American manufacturing capacity filled the gap. Once complete, the pipe snaked along concrete guttering out of the factory buildings onto a stack of finished pipeline 3/4 of a mile long. A conundrum would be towed to a special dock where it was held by 2 steel arms. A sprocket chain, driven by an electric motor, slowly rotated the drum. Pipe was fed from an overhead gantry. As the conundrum rotated, the pipe wound around it. At the end of each 4,000-foot segment, the next was welded in place. Workers cleaned out the swarf. The process continued until the conundrum held 90 miles of pipe. The work was meticulous. It was repetitive. And it was absolutely vital. The towing trials for the conundrums presented their own challenges. Initially, diesel tugs were used. These were the most modern and therefore believed to be the most powerful. However, engineers discovered something counterintuitive. When tested by pulling against a spring balance anchored to a bollard on the quayside, the diesel tugs performed well, but steam tugs performed better. The nature of a steam engine provided maximum torque at low speed, exactly what was needed for towing a 1,600-ton floating drum at walking pace. The diesel tugs pulled adequately. The steam tugs pulled the bollard out of the quay entirely. Steam tugs were selected for the actual channel crossings. An Admiralty hopper barge named W-24 was converted to carry a conundrum and christened HMS Persephone. She was a twin-screw vessel, 200 feet long and 35 feet wide. On June 4, 1943, Persephone conducted a trial lay of 1 mile of Hamel pipe. Complete success. Though not having the capacity to cross the channel, Persephone proved the concept. She went on to lay 16 Hamel pipes across the Solent to the Isle of Wight. Each lay was a rehearsal. Each rehearsal revealed new problems. Each problem required new solutions. The engineers learned that Hamel pipe would last approximately 6 weeks in seawater before corrosion became critical. Fluorescent dye was added to the fuel. Patrol aircraft could spot the bright green marker if leaks occurred. Testing revealed another limitation. Hamel pipe was too stiff for shore-end connections. It couldn't be deployed quickly enough, especially at the French end, where operations would occur under heavy enemy fire. The solution: use haze cable at both ends of each Hamel pipeline. The flexible lead cable could be maneuvered quickly. The rigid steel would carry the bulk of the distance. Two technologies combined into one system. By April 1943, both Haze cable and Hamel pipe had successfully completed their main trials. The technology was proven. Now came the harder part: actually deploying it. Section 5. The invisible infrastructure. While engineers wrestled with pipelines, a parallel construction program was transforming southern England's landscape. Operation Pluto required more than underwater pipes. It required pumping stations, storage facilities, land-based pipeline networks, and all of it had to remain invisible to German reconnaissance. The Petroleum Warfare Department selected 2 primary pumping station sites: Sandown on the Isle of Wight and Dungeness on the Kent coast. Construction occurred at night. Equipment was transported under tarpaulins. Every activity was designed to avoid aerial detection. But the stations themselves presented a problem. Powerful pumps required substantial buildings. Substantial buildings attracted attention. The solution was pure British ingenuity: disguise. The pumping stations were hidden inside ordinary-looking structures. At Dungeness, one station became Brown's ice cream shop, complete with painted windows displaying frozen treats. Another transformed into a bungalow, whitewashed and charming. A third became a garage. A fourth resembled a gravel quarry office. On the Isle of Wight, pumps were installed inside the ruins of the Royal Hotel at Shanklin. Other stations occupied civilian seaside buildings, deliberately neutral and made up as shops. Some appeared to be fishermen's cottages. Others looked like 1930s residential homes. All were uninhabited. All concealed massive pumping machinery. Each station was equipped with 30 diesel-powered reciprocating pumps, capable of 180 long tons per day. 4 large Byron Jackson Company electric centrifugal pumps added 3,500 long tons per day capacity. Combined output, 400,000 imperial gallons, at 1,500 pounds per square inch pressure. The stations were fed by the Avonmouth-Thames pipeline system, a 1,600-kilometre network of underground pipes constructed almost entirely at night to prevent aerial detection. This network transported fuel from ports at Liverpool and Bristol, safely distant from German bombers, down to the Channel coast. The Liverpool end of the pipeline terminated in the River Mersey. A platform was constructed there. American and English tankers would tie up and connect their delivery hoses. The fuel flowed south through 1,600 kilometres of buried pipeline. Every kilometre was laid at night. Every section was camouflaged. Every connection was tested. The work was backbreaking. Men dug trenches by hand in darkness. They laid pipe by feel as much as by sight. They worked through rain, cold, and exhaustion. They never knew what the pipeline was for. They only knew it was important. A 70-mile branch line connected Dungeness with its eastern terminal at Walton-on-Thames. Sandown was connected through a 22-mile link between the Isle of Wight and Fawley refinery. The entire system was completed by March 1944. But the deception didn't stop at pumping stations. As part of Operation Fortitude, the massive deception plan to convince Germans that the invasion would target Pas-de-Calais rather than Normandy, a fake oil dock was constructed at Dover. The facility was built from camouflage-painted board, sewage pipes, and fiberboard. It featured false pipelines, fake storage tanks, a pretend fire brigade, dummy anti-aircraft guns. King George VI himself visited to inspect the fake facility. The Lord Mayor of Dover publicly mentioned it as a potential municipal asset after the war. German reconnaissance aircraft photographed it repeatedly. They saw exactly what the British wanted them to see: massive fuel preparations for an invasion across the Strait of Dover to Calais. They never imagined the real pipelines were being prepared 150 miles to the west. Any materials transported to the various Pluto facilities required asking for Captain Jones before entry was permitted. The fictional captain became a legend among workers who never questioned his absence. Security was absolute. Corby steelworkers producing the Hamel pipes knew their product only as Project 99. They weren't told what it was for. They weren't told where it went. They weren't even told it was a pipeline. Years after the war ended, many learned for the first time just how important their work had been. Section 6. The Bristol Channel Dress Rehearsal. Before crossing the English Channel, Pluto needed a full-scale rehearsal. December 1942 provided the opportunity. HMS Holdfast, a merchant ship specially modified for cable laying, was loaded with 30 miles of 2-inch HA's pipe. Commander Henry Treby Heel took command. Aboard to monitor the test were the operation's key figures: Mr. Hartley from Anglo-Iranian Oil, Mr. Toombs also from Anglo-Iranian, Mr. Colby from Iraq Petroleum, Mr. Betson from the Post Office, Commander Hardy from the Admiralty, and Mr. Whitehead from Johnson and Phillips, who had designed the pipe handling equipment. The destination, the Bristol Channel between Swansea and Ilfracombe. Distance, approximately 50 kilometres. The crossing would simulate the actual channel deployment. On December 26, 1942, Holdfast began laying pipe. The weather was atrocious. Rough seas battered the vessel. Winds gusted unpredictably. Perfect conditions for testing. The crew worked through Christmas. By December 30th, the 30-mile length was laid successfully. Shore ends were connected at Swansea and Ilfracombe. But the real test came afterward. The pipeline's sturdiness was proven when 2 German 500-pound bombs were dropped on Swansea, just 100 feet from the cable. The pipeline survived without damage. Then a ship's anchor dragged across the cable. Holdfast located and repaired the damage. Pumping operations began, first at the original design pressure of 750 pounds per square inch, then at 1,500 pounds per square inch. The cable delivered 56,000 imperial gallons of fuel per day, continuously, without failure. The rehearsal was an overwhelming success, so successful that engineers immediately upgraded their ambitions. The decision was made: upgrade from 2-inch to 3-inch diameter pipe. Fewer pipelines, greater capacity, better efficiency. The Bristol Channel pipeline continued operating, supplying parts of Devon and Cornwall for the next year. It became more than a test. It became a training facility. Royal Army Service Corps and Royal Engineers personnel practiced petrol pumping operations. They learned the equipment. They perfected techniques. They prepared for the invasion of Europe. All from a pipeline that was never supposed to be permanent. Section 7. Bambi and Dumbo. The Pluto operation was divided into 2 separate pipeline systems, each with its own Disney-inspired codename. Operation Bambi would connect Shanklin on the Isle of Wight to Cherbourg in Normandy. Distance 70 miles. Operation Dumbo would connect Dungeness in Kent to Boulogne in Pas-de-Calais. Distance 31 miles. Bambi was designated for first deployment. The logic was sound. Cherbourg was the major port nearest the Normandy beaches. Capture Cherbourg, establish the pipeline, and fuel would flow directly to the advancing armies. The original planning for Operation Overlord aimed to capture Cherbourg by D+8, 8 days after D-Day. Pluto would begin pumping by D+112. Full functionality would be achieved by D+75. It was a tight schedule. But the plans, as Eisenhower himself noted, rarely survive first contact with reality. D-Day occurred on June 6, 1944. 200,000 men and 20,000 vehicles poured onto the beaches of Normandy. The invasion was the largest amphibious operation in military history. 5 beaches, 5 simultaneous assaults, paratroopers dropping behind enemy lines, naval bombardments shaking the earth, and through it all, the fuel question loomed. In the initial stages, fuel came in 20-liter jerrycans and 44-gallon drums. An entire American manufacturing plant had been shipped to the London area to produce enough jerrycans. By 1944, Britain had stockpiled 250,000 tons of packaged petrol and diesel fuel. But jerrycans were a stopgap. They required enormous labor to load and unload. They cluttered beaches with empty containers. They couldn't sustain a continental campaign. Cherbourg was supposed to fall quickly. It didn't. German defenders fought with unexpected ferocity. The port wasn't captured until D+21, nearly 2 weeks behind schedule. And when it fell, the damage was catastrophic. German demolition teams had systematically destroyed the port facilities. Fuel deliveries couldn't begin until D+49. Bambi was already hopelessly behind schedule. In the meantime, fuel was supplied through smaller ports using coastal tankers. But the systems were improvised. Tombola lines, ship-to-shore pipelines, had a tendency to break. The channel tankers, Chance, fared poorly in rough weather. By late July, 16 Chance were laid up for repairs at a special tanker repair facility at Hamble-le-Rice. Consideration was given to cancelling Pluto entirely. But the alternative was worse. The operation proceeded. Section 8. The disasters of August 1944, August 12, 1944. HMS Latimer began laying the first Haas pipeline from Cherbourg to the Isle of Wight. The ship was a converted Liberty ship, displacing 12,120 long tons. She could carry 100 miles of 3-inch cable, weighing approximately 6,400 long tons. Captain Hutchings coordinated the operation from the lead vessel. The weather was cooperative. The seas were calm. The crew worked with practiced efficiency. The cable paid out smoothly from the ship's hold. It sank gently to the channel floor. The lay took just 10 hours. 65 miles of pipeline deployed successfully. The crew was jubilant. It should have been a triumph. It was a disaster. Before the pipeline could be put into operation, an escorting destroyer's anchor caught the cable. The anchor chain tangled in the pipeline. The destroyer dragged the cable. The thin lead core couldn't withstand the lateral stress. The damage was beyond repair. 65 miles of carefully manufactured cable destroyed by a single mistake. Months of factory production, thousands of man-hours of labor, tons of precious lead, all lost to one anchor. The crew's elation turned to despair. 2 days later, HMS Sancroft attempted the same crossing. The lay was successful, but during the shore connection attempt at Sandown, the pipe became wrapped around the propeller of the support ship, HMS Algerian. Another pipeline destroyed. August 27, 1944, engineers decided to try Hamel pipe instead. HMS Conundrum 1 was towed into position. The crew attempted to begin rotation. The drum wouldn't move. 10 tons of barnacles had attached themselves to the submerged portion of the Conundrum. The marine growth prevented rotation entirely. Workers scraped off the barnacles by hand. Another attempt was made days later. The pipeline broke about 29 nautical miles out. Each failure was a body blow. September 22, 1944. Finally, a success. HMS Sancroft laid a Hayes cable that worked. The pipeline was commissioned, delivering 56,000 imperial gallons of fuel per day to the United States armies. September 29, 1944. Conundrum 2 completed a successful lay of 3-inch Hamel pipe. 2 pipelines operational. Hope returned. October 3, 1944. Pressure was increased from 50 to 70 bars, 730 to 1,020 pounds per square inch, to boost fuel volume. Both pipelines failed. The HI's cable failed due to a faulty coupling. The Hamel pipe broke when it encountered a sharp edge on the ocean floor. Operation Bambi was terminated the following day. Total fuel transferred, approximately 3,300 long tons, 935,000 imperial gallons. Less than 3 days' worth of fuel for the Allied armies. The official history would later state, Pluto contributed nothing to Allied supplies at a time that would have been most valuable. But the engineers weren't finished. They had learned. And they had Dumbo. Section 9. The Dumbo Triumph. With Bambi abandoned, all Pluto efforts shifted to the Strait of Dover. The reasoning was compelling. The distance from Dungeness to Boulogne was only 31 miles. Less than half the Isle of Wight to Cherbourg route. Shorter distance meant fewer failure points. Shorter distance meant faster deployment. Shorter distance meant lower pressure requirements. And the British 21st Army Group, advancing through the Low Countries, was in pressing need of fuel. October 10, 1944. HMS Sancroft laid the first Dumbo pipeline, a 3-inch AES cable, in just 5 hours. The pipe was connected to a beach in the outer harbour of Boulogne, 23 nautical miles distant. The original plan called for Ambleteuse as the terminus, but the beach there was heavily mined. Boulogne involved longer distance and more difficult approach, but cable-laying techniques had been refined through months of painful experience. October 26, 1944. The Dumbo system began pumping. It worked. It kept working. Over the following months, engineers laid pipeline after pipeline. HMS Sancroft and HMS Latimer laid 9 3-inch and 2 2-inch HAIS cables across the strait. 6 3-inch Hamel pipes were laid by the Conundrums. Total, 17 pipelines. Total length, approximately 500 miles of underwater pipe. By December 1944, Dumbo was providing 1,300 long tons of petrol per day. January 1945, 305 tons per day. March 1945, 3,048 tons per day, a tenfold increase from January. March 15, 1945, Dumbo surpassed its target of 1 million imperial gallons per day. That milestone represented more than just a number. It represented vindication. Every skeptic who had declared the project impossible, every failure in August 1944, every barnacle-encrusted conundrum, every pipeline snapped by anchor chains, all of it led to this moment. April 3, 1945, the system peaked at 4,500 long tons per day. That's 4,000 tons, almost 1,000 imperial gallons, flowing invisibly beneath the English Channel every single day. To put that in perspective, 1,000 gallons is enough to fill 50 average swimming pools. Every single day. Without pause, without failure, without detection. And the Germans never knew. Not one pipeline was detected. Not one pipeline was attacked. Not one drop was lost to enemy action. The secrecy was absolute. German reconnaissance aircraft flew over the channel daily. They photographed the fake oil depot at Dover. They monitored the phantom Fusag army group. They watched the dummy landing craft. They never spotted the thin lines of pipe trailing from tugboats across the strait. They never questioned why fuel was flowing to Allied forces faster than tankers could deliver it. They never imagined that beneath their submarines, beneath their mines, beneath the waves they thought they controlled, petroleum was flowing at rates that would sustain an entire army group. The fuel flowed north through France, connecting to an inland pipeline system that extended from Boulogne to Antwerp, Eindhoven, and ultimately to Emmerich on the Rhine. The pipeline didn't stop at the Channel. It kept going, following the advancing armies, supplying fuel wherever it was needed. By the war's end, fuel was flowing from Liverpool all the way to the Rhine, a continuous pipeline of over 1,600 kilometers. Royal Engineers officer John Gillespie, then a young lieutenant, later recalled his experience with Pluto. "We were pumping 1 million gallons of petrol a day all the way from Liverpool across the Rhine at Emmerich," he remembered. "We supplied the British Army, the Canadians, and the Americans. We also pumped aviation spirit to an airdrome at Carpiquet, where the RAF were able to land their fighter jets." Gillespie was responsible for the construction of army installations for the operation. He understood the scope like few others. The pipeline didn't just fuel tanks, it fueled aircraft, it fueled the entire Allied advance. At age 101, Gillespie recalled Pluto as one of the most significant moments of his life. By the end of the war, the Pluto network had carried 180 million imperial gallons of petrol, 820 million liters. 8% of all petroleum products sent from the United Kingdom to the Allied Expeditionary Force in Northwest Europe. Total fuel delivered to the Allied Expeditionary Force, approximately 5.4 million long tons. Pluto's contribution, 370,000 long tons. Total cost of Operation Pluto, $4,428,000. Return on investment, incalculable. Section 10. The Legacy, August 7, 1945. The Pluto system was finally closed down to save manpower. The war was over. The pipelines had carried their last gallon. August 31, 1945. Operation Pluto was officially disbanded. The Petroleum Warfare Department was wound up on March 31, 1946. The Tilbury plant was transferred to the Admiralty. All remaining stores went to the Ministry of Supply. No post-war use of the technology was contemplated. This decision was deliberate. The war was over. The immediate need had passed. The technology was specialized for a specific mission that had been completed. Operation Pluto's records were sealed and sent to the Public Record Office. They would remain classified for 30 years. During those 3 decades, the story of Pluto faded from public memory. The workers who had manufactured the pipes went back to civilian life. The sailors who had laid the cables returned to merchant service. The engineers who had designed the systems moved on to other projects. Few people knew what had happened. Fewer still were allowed to talk about it. The security classification ensured that one of the war's greatest engineering achievements remained virtually unknown. When the records were finally unsealed in the 1970s, historians began piecing together the full story. They discovered the scale of the operation. They found the technical specifications. They read the after-action reports. They learned about the failures and the successes. And they marveled at what had been accomplished. The 30-year secrecy served a purpose. It protected the engineers and their methods during the Cold War. It prevented the technology from being exploited by potential adversaries. But it also meant that the men who had built Pluto never received the public recognition they deserved during their lifetimes. Many died without knowing how widely their achievement would eventually be celebrated. The Royal Commission on Awards to Inventors convened to recognize the men behind the operation. Tax-free payments were awarded. Arthur Hartley, $9,000. Bernard Ellis, $5,000. M.K. Purvis, designer of the conundrum, $85,000. A.E. Price, who designed the wedge-gripping device for shore connections, $250,000. Hartley also received appointment as Commander of the Order of the British Empire in 1944. The United States awarded him the Medal of Freedom in 1946. He retired from Anglo-Iranian in 1951 and became president of the Institution of Mechanical Engineers. He died in 1960, 3 months into his tenure as president of the Institution of Civil Engineers. Between September 1946 and October 1949, over 85% of the pipeline was salvaged and scrapped. The salvage operation itself was an engineering challenge. HMS Latimer and HMS Holdfast, now renamed Empire Ridley and Empire Tor, retrieved their own handiwork. These ships had laid the pipelines. Now they pulled them up. There was a certain poetry in that symmetry. Empire Tignes, a former German tanker pressed into British service, joined the salvage fleet. Wrangler, an ex-Admiralty Mark III tank landing craft, contributed its shallow water capabilities. Redeemer, an ex-Admiralty motor fishing vessel, worked the difficult shore connections. The crews worked methodically. They traced each pipeline across the channel floor. They carefully raised the cables and pipes. They coiled them back onto the same ships that had laid them. In all, 22,000 long tons of the original 23,000 long tons of lead were recovered. 3,300 long tons of the original 5,500 long tons of steel were pulled from the channel floor. 75,000 imperial gallons of petrol were still in the pipelines, recovered along with the hardware. The fuel had remained in the pipes, uncontaminated, for over a year. A testament to the engineering quality. The value of the salvaged materials exceeded the recovery costs. Total value, approximately $400,000. In today's currency, that would be over $15 million. The salvage paid for itself, and then some. But the real legacy wasn't in the scrap value. It was in the technology. Operation Pluto was the world's first undersea oil pipeline. The engineering accomplishments pioneered techniques that would revolutionize the offshore oil industry. Composite flexible pipe, coiled tube reel laying, high-pressure subsea operations. All trace their lineage to those 3-inch cables laid beneath the English Channel in 1944. By the 1960s, the World War II engineering feat of reel laying began reappearing in the offshore industry. The massive towed conundrums receded into history, but coiled pipe reels now ride aboard specialized vessels. In 2007, the MV Solitaire set a world record for ultra-deep pipeline installation, reaching depths of 9,100 feet. The ship could hold more than 22,000 tons of 60-inch diameter pipe. It could lay almost 6 miles of pipe in a single day. The direct descendant of those first 30-foot conundrums, towed by tugboats across the channel. Today, over 45,000 kilometers of offshore pipeline exist in the UK sector of the North Sea alone. Another 45,000 kilometers run through the United States Gulf of Mexico. 8,800 kilometers crisscross the Norwegian North Sea. All of it, every kilometer, every joint, every pumping station, traces its heritage to Hartley's impossible idea in April 1942. Resolution. The story of Operation Pluto is not a story of unqualified success. Bambi failed spectacularly. Dumbo arrived too late to effect the Normandy battle. Only 8% of Allied fuel came through the pipelines. The official history was blunt. Pluto contributed nothing to Allied supplies at a time that would have been most valuable. And yet, General Eisenhower called it second in daring only to the Mulberry harbors. He wrote that the pipelines provided our main supplies of fuel during the winter and spring campaigns. 172 million gallons of fuel, 180 million imperial gallons, 820 million liters. All flowing invisibly beneath the English Channel, all completely undetected by the enemy, all delivered without a single combat loss. Arthur Hartley's impossible pipeline worked, not perfectly, not on schedule, not in the way anyone planned, but it worked. And in working, it proved something fundamental about engineering. The impossible is merely the not yet attempted. Today, visitors to Dungeness can still see Pluto Cottage, the camouflaged pumping station now operating as a bed and breakfast. Guests sleep in rooms that once housed diesel pumps. They cook breakfast where engineers once monitored pressure gauges. They relax where fuel flowed at 1,500 pounds per square inch. On the Isle of Wight, the former pumping station at Sandown is a miniature golf facility. Families putt golf balls over ground that once supported massive centrifugal pumps. Children play where serious men once won a war. At Shanklin Chine, a surviving section of the pipeline remains on display. The 3-inch HAIS cable, with its layers of lead, steel tape, jute and wire, sits as a museum piece. Visitors can see exactly what those engineers built. They can touch the materials that carried 180 million gallons of fuel. The Romney Marsh wartime collection at Brenzett houses a permanent display related to Pluto. A fully restored Pluto pump is on display at the Bembridge Heritage Society and Centre on the Isle of Wight. These quiet monuments remind visitors that beneath the charm lies machinery that helped win a war. The pipeline itself is gone, salvaged, scrapped, recycled into post-war construction. But 10% of it still lies beneath the channel floor. Remnants of Operation Bambi, silent testimony to an engineering feat that most people have never heard of. The men who built it, Hartley, Ellis, Hammock, the thousands of workers at Corby Steelworks, the crews of HMS Latimer and HMS Sancroft, they understood something that transcends their moment in history. Innovation doesn't require perfection. It requires persistence and the courage to attempt what experts declare impossible. Hartley stood in that conference room in April 1942, listening to brilliant minds explain why his idea couldn't work. He built it anyway, and in building it, he changed the world. One pipeline at a time, 1 gallon at a time, one impossible idea at a time. That is the true legacy of Operation Pluto. Not 180 million gallons of fuel. Not 500 miles of pipeline. Not even the victory those pipelines helped secure. The true legacy is simpler. When someone declares something impossible, the proper response is to ask, has anyone actually tried? Arthur Hartley tried, and history remembers, history remembers, history remembers, history remembers, history remembers, history remembers, history remembers.